Thank you.
I guess it's one. I was only one person who didn't know what is the game because everyone probably else knows. So why you describe the game for completeness?
No. Just not everyone knows what it is.
Not everyone knows. Then explain what is the game.
Okay. I'd like to give a talk about my results about computational bounds for the 2048 game. I will first briefly describe the rules of the game. For those who are not familiar. In the game, originally we have a field 4 by 4. In each cell, the cell may be even either empty, or it may contain a tile 2, 4, 8, 16, and so on, a power of 2.
Yeah, strangely, 1 is not there. But...
Sorry?
No, it would be natural to start with 1, but for some reason they start with 2.
Yes, I don't know the reason, it's just the original rules, but it turns out that almost always the results don't depend on whether we start with 1 or 2 tiles and which are the tiles.
No. I want to say different thing, that we can start with instead of 2, 4, 8, we can have 1, 2, 4, and so on. Because just powers of 2 normally starts with 1, but and how they select the initial tiles? They are put randomly or how?
Yes, randomly, and always each new tile appears in a random free cell, but it is 2 with probability 90% and 4 with probability 10%. These are the rules.
Mm-hmm. So initially we start with two tiles which have definitely 2 and 4, yes?
No, they are also each tile is 2 with probability 90% and 4 with probability 10%. Mm-hmm. And the 2 cells are selected uniformly at random. But it turns out that it doesn't really matter whether we start with 1 or 2 tiles and which tiles and where they are located. Okay, for all cases where I was looking at the probability and at whether the game is winnable, a particular tile is reachable, it didn't depend on this. But of course, I have no proof of it. So I will proceed with the explanation of the game. This is an example of an initial state. Can you see my cursor?
Yeah.
Yes.
Pointer. Okay. Well, initially we have 2 tiles at random locations, and let's say each turn we can swipe either left or right or up or down. If we swipe, for example, down, these 2 tiles move until they meet the border or until they meet another tile. In this example, 4 moves to this square and 2 moves to this square, and the new tile appears too. Also, there is a requirement that if nothing changes when you swipe, this move is not allowed.
And say it again, when the new tile appears, it also with probability 90% 4, 2, right?
Yes. Okay, for example, then we decided to swipe right, and here's the position we got. This 2 goes here, this 4 goes, this 2 stays on its place, and this 4 goes here because here is 2.
So they fall in the direction prescribed, and the new tile appears in the random place.
Yes. But
so the only way when the move doesn't change anything is if everything is full, because otherwise a new tile will appear, yeah?
No, it's not the case. For example, okay, we don't have such an example here, but imagine that the first 2 rows are filled with numbers except the last cell, for example. And no, the first two rows are filled with numbers, and say they are all distinct, but this and this number are 2.
Yeah.
Then if you swipe, then for example, you can't swipe up because this won't change anything.
But this will create new cell, no?
No, it won't, because your move will not be allowed.
Ah, so additionally, just the swiping should change something. So, for example, let me check that I understand correctly. Imagine the second example, in the middle example, in the upper row, this tile 2 appeared in the bottom here. Yeah. Then we cannot move down.
Yes,
it is not allowed.
I don't know why the authors decided so, but it's a rule of the game. And this rule, unlike the initial configuration, does sometimes substantially influence the results. Okay, for example, then after this configuration, we decided to swipe down. These tiles 2 and 2, they merged into one 4. In general, the rule is whether 2 tiles of the same number collide, they merge into one, which is double each, which has a number of that is twice the number on each tile.
For example, if there were 3 tiles, if there are in the last column 2, 2, 2, then it probably becomes 4, 2, but 2, 4 or 4, 2.
4, 2. It is made in the following way. We start with the nearest to the border tile. It goes in the prescribed direction unless it meets, for example, the border. Then the second tile, it goes in the prescribed direction, and if possible, it merges with the tile there. And if there were another 2, it would have
just fall down.
Yes, it would be the third.
Excuse me, we have a message in the chat from Sasha Kozachinsky. He's saying that he almost cannot hear the speaker. Is it the local problem, or everyone has this? For me, it's not terribly good, but acceptable.
Okay, maybe I can try the following thing. My laptop doesn't have a microphone, or it is broken, so I use the microphone of my headphones, but I can try to use the microphone of my phone. This way I can join as a second.
Okay, you can just use 1 minute to try this. If it doesn't work, then we continue like this. If it works, it will be nice.
Okay.
Yeah. Meanwhile, I can say that there is if we have, for example, a full column of 4s, it's probably we will get full column of 2, 2, 2, 2, 2. Then we have twice 4, probably, yeah, or not?
Yes, it's true.
So everything is
Sasha, have you tried already this game?
Yeah, and even I got more than you.
So how much have you got?
1,000 something.
Oh,
no, but I did random things, so it's not. But I get something like this twice.
Twice? Oh.
Twice, yeah.
For me, it seems impossible.
But okay, if you understand what is going on, then please explain how to play this game. How can you win all this money, and so what is going on?
You don't get any money. You get only satisfaction, and then you just push one of the 4 arrows on the keyboard, and then something happens.
So my choice is the direction of this.
The only thing you can choose is the direction. And there is some luck, probability luck, depending on where the new tiles appear.
And we are going to explore whether this luck is in which cases it is essential, and to which extent does it include our ability to achieve high tiles?
Yeah,
the first result is we can always achieve
excuse me. Just there is a message in the chat that that people are still not terribly happy, but they say that if one can make marks on the slides, then it could the things could be easier to follow.
Okay, let's finish story with the microphone.
Yeah,
that works or not, because it would be.
No, apparently.
Unfortunately, I was unable to join from my phone because the Zoom app crashes there.
Okay, that is not important. Why? Just you cannot. Okay, so up to now the rules of the game were explained, and the result is that first a deterministic result that you always can get some number. I forgot which, but thousand or something. And second, with very high probability, you can get some bigger number.
Yes, exactly. My first part of the talk will be about that we can always get some number. This number turns out to be 256. It's not very high number, but okay, I will elaborate on it a bit later. First, I want to say that, like most games, there are some space completeness results, but it's not the topic of my talk. I just want to mention that, as far as I know, determining whether one position is reachable from another is a space complete problem.
But I don't understand. It seems to be an NP problem. How can it be space complete? If you have a sequence of moves, each time you get a new thing. No, of course you consider probably n times n thing, not 4 times 4. But anyway, the number of moves is n square mostly.
I guess the statement is somewhat adversarial. I mean, when you are playing as the user and tiles appear in any way, and whether you can guarantee that you can reach one position from another.
Okay, and do you know this proof? Because it's interesting. Okay. So there is some unclear rumor about this, but if you at some point know the proof, it will be an interesting thing to explain it to us, because we understand what is space and why it's more or less equivalent to games, but some specific game analysis for this case will be maybe interesting. So just think about this. Okay,
so just my point was that as it is with many games, there are some proven space completeness results about them, but I just didn't want to stop on them because I am not really an expert in the field. I mean, I didn't analyze any of the proofs.
Yeah. But it won't hurt if you, at some point, we will be glad to hear your explanation if you decide to study this. Okay.
There are also some heuristics, and the best I found is the following page on GitHub. The author claims to reach these tiles with these probabilities. It's a very high probability for achieving 32,000, and 3%, which is also very high for this tile, 65,000. Actually, the maximum possible tile in the game, if you are very lucky, is twice the 65,000. No, because it's 2 to the power of 17, because 16 is the number of tiles, and if you are lucky, you can. Okay.
No, it's obvious that you cannot get too much, because when you get a bigger tiles, you need smaller ones, and so you are out of.
Yes, at some point you have to have all the tiles starting from 2 or 4 up to your largest tile, and that's why the theoretical possible maximum turns out to be 2 to the power of 17, and in fact the probability of reaching it is obviously not more than 10%, because when you are trying to reach it, you have to go through a position where in a cell exactly 4 should spawn. So the tile 131,000 something, it is reachable with probability less than 10%, at most 10% of the time. But as far as I know, nobody has ever reached it, even using a computer playing fairly. Okay. Anyway,
but in cooperative setting, it is reachable.
Yes, in cooperative.
So the probability is positive, but just maybe very small.
Yes, the probability is probably very small, and it turns out, surprisingly, that the probability of achieving the previous tile, 65,000, is already 3% at least, because we have a strategy that achieves it 3% of the time. It is some alpha beta pruning of depth 7. It doesn't use neural networks, but it uses heuristics. So it's like some heuristic wrapped into alpha beta pruning.
Yeah, it's not very clear. What probably some people know about alpha and beta pruning, but usually it's used in the context of adversarial game. So adversary game. So it's not very clear if it's a randomized thing. What is how do you understand this? But okay, maybe you will go and explain it later when you explain your bound.
Okay, let's proceed. Yes, I understood your point. Maybe I was wrong about alpha beta pruning.
Okay, let's then go to your results.
I mean, you are not wrong. If you get to 3% of that high tile, you are kind of forced to treat probability as your enemy anyway.
I don't understand this.
Well, you should expect that probability plays against you in a sense.
No, if there is an opponent, maybe we are even not able to reach this. It's if the probability is very small, is smaller than 1, then this means that in the opponent setting there is a strategy for the opponent. So I don't understand what you say. Okay, but maybe we can return to this later when we see.
I'm sorry about alpha beta pruning. It seems like you are right, and it uses an algorithm called expect-max algorithm. As I understand, it selects the best move that has the best expectation of the maximum of the best expectation, and so on.
Yeah. Okay. So if you didn't do this, let's postpone this to the end.
Okay. So we have a question: whether optimal probability of reaching the original goal in the original setting is 1 or not. We don't know. Probably not, but all we know now is that it's at least 0.99969, and we don't know whether it's exactly 1 or not, but probably not.
This is your result. Your bound 0.999.
Yes, the bound is my result.
Yeah. Okay. Yeah.
Okay, let's consider the game as a two-player game that is adversarial setting, that the first player makes a swipe, the second player adds a tile, and so on. In this game, we have to analyze who wins the game.
And probability 1 means that in two-player game, the first player has a winning strategy.
Yes, exactly.
For obvious reasons. Yeah.
I have computed on a laptop the following tiles are the maximum tiles for which the game is won by the first player, and if a tile greater than this is chosen as the goal, then the second player wins. For example, on 3x3, 32, the first player can reach 32 guaranteed, but 64 not always.
Mm-hmm.
But with
so when you write some numbers, they are both upper bound and lower bound.
Yes, here, yes.
And if you write a question mark it means that you don't know neither the upper bound nor the lower bound.
In fact, no. Just a second. In fact, 3 by 5 turns out to be 128, and in this case, getting upper bound was harder than getting the lower bound because the graph was significantly larger. But the lower bound took 3,000 core hours.
You mean that you used some parallel computation on a server, or you just waited very long?
No, of course I used a parallel computation. That time it was a machine with 32 cores, but that is not the maximum which was used in these results. Okay, the upper bound was achieved only recently using another machine which has a GPU, because I can program on a GPU and I have access to a machine with a very good GPU. That's why I was able to perform some useful computations, in particular bounds for this game. Okay, and
the other question mark, 4 times 4, still there is no proven. So that's proven bound is 256, and the upper bound is just this 65 something, maybe.
Yes, it seems like I haven't seen an upper bound. It seems like there is no meaningful upper bound here, but lower bound is 256. Okay. In order to prove that 256 is not reachable on 3 by 5, it's a smaller field. And in fact, it is a little more uncomfortable to play on 3 by 5 than 4 by 4. Because, not only because it has one cell fewer, but also because, okay, maybe I can't explain it, but just some of the, I just wanted to prove that 256 is not reachable on 3 by 5. And for that to be done, you have to consider about 35 trillion positions. That is okay to traverse such a graph, but it doesn't fit into memory of any adequate computer. Let's make some observations. The first observation is that on each user's turn, the total time
before you speak about observation, so it's well over RAM size, so you need some special trick and you succeeded to prove it, or you explain why you were unable to prove it.
No, in this case, it's 3 by 5 and about 256. I was able to prove it using some tricks.
256 is not reachable, but this requires special tricks. And now what you are doing is explaining the tricks.
Yes, in some sense.
Yes, I just want to understand the structure of what is happening now. Okay.
I just want to, because 256 is the first. Okay, never mind.
Okay, so what are these special tricks? You made 2 observations. Explain us.
Yes, in fact, it's not hard to make these observations, and the first thing that we use is pretty clear. Okay, let me explain. The first observation is that when it's the user's turn, the total sum of tiles on the field doesn't change.
Because 2 4s combines to 8, for example, and the sum is the same. Good.
Yes, and the second observation is that whether there's computer's turn, the total sum of tiles on the field increases by 2 or 4.
Yeah, also clear.
Yes. And the suggestion is to split the game graph into layers of fixed sum and whose turn is now. For example, a layer of all positions with sum 200 and where it is user to move.
Yeah, so there are layers, and then we can the computer move is adversary moves us to next layer onto the layer next to plus 2 or plus 4, and the user turns only moves inside the layer.
Yes, but I decided to split these layers. I decided to say that, for example, sum4 and user's turn is a different layer than sum4 and computer's turn.
Ah, yeah, okay, yeah, sure.
But they're of the same structure.
Yeah.
Okay, here is an overview of our game graph, how it splits into these layers. And now we have a good thing to know is that we only have to store 3 layers at once in memory in order to compute who wins the game. It can be done this way. For example, if we have the layer with user where there is user to turn and the sum is 6, and the layer with sum 8 and user to turn, we can compute anything in the layer of computer with sum 4.
Yeah. So it's kind of, if we just use the standard procedure of assigning the winning, losing things with this way, since we need only 2 next layers, so we use 2 layers to fill the third one. Yeah?
It should be done a bit more accurately, because the 2 next layers is in fact 4 next layers, because they are double.
Ah, you count, yeah.
So in this way you will obtain not 3 but 5, but it is easy to show that 3 is sufficient. Okay. This way it allows us to compute more than before, but it's not the end. Let me show
what are these numbers?
Yes, these numbers are field and tile which we have to reach, for example, 3 by 5 and tile 128. Then the total size of the game graph and maximum size of one layer. B is billion and T is trillion. That is 1,000 billion.
But can you explain why the switching from 108 to 2 tile? Oh, it's sum. Sorry. It's not the maximal tile. It's sum. Yeah. So they're bigger. Also, an idiotic question. So probably if you start close to the end, some layer which is close to the right to the maximum, you can use just full exhaustive search to fill one cell, because the 3 starting from this point is not so big.
You may, but it seems like, since our algorithm is linear in the size of the graph, we don't have the need to make this adjustment to it. It seems like we can simply traverse layer by layer, starting from the layers with the largest sum, and store 3 layers in the memory.
What I'm saying, so do I understand correctly that the layer with the largest sum is the biggest layer, or not?
No, I'm sorry, there is a typo. I mean, it's not sum, it's the goal tile here. So each line is one game.
Yeah. But what I'm saying, that maybe you can start with some intermediate layers, not to store in the memory the maximal layers, but make the full search to compute some data for some intermediate layer, then combining dynamic programming with just full search, and this way you can kind of compromise the requirements for memory and time.
So you propose to start in layers with high sum and prove that all the layer contains only lost positions, yes?
No. I proved to start with some intermediate layer, which is
before or after the peak? Okay, I
didn't
say the peak, about the peak.
There is a peak in layers. No. Of course, it could be. It is useful only before the peak. Okay.
Yes, it turns out that, for example, on 4x4 and go to 156, I will show the distribution a bit later.
Just continue. Sorry.
It's included in the presentation. I will
Yeah. Okay. Just continue.
Okay. Just I wanted to highlight that the maximum layer size is much smaller than the total size of the game graph. That's why many games become feasible after this peak. For example, okay, there's also one thing to notice. I also added the amount of RAM you have to have in order to traverse this graph, storing 3 layers at once. And for example, in the first case, there is the maximum layer size is about 45 billion positions, and it requires 18 gigabytes to store 3 consecutive layers in the worst case. In fact, it turns out that yes, there are 3 layers with almost maximum size, and they are consecutive. Because, okay, it will become clear after I will show the picture of the distribution.
Yeah, sorry for again, but why the total requires less memory than the maximum layer size? What is that?
Yes, because byte is 8 bits, and we can compress it all to take only 1 bit per position.
So it's billion of not bits, but
gigabyte. Yes, it's a billion of bytes. That is 8 billion of bits.
Yeah. Okay.
Yes, and it turns out, for example, 3x5 sum 128 requires only 18 gigabytes of RAM, and it was possible to traverse this graph on the server, but okay. In the next case, we need 76 gigabytes on a machine where I conducted the experiment. There was only 64 gigabytes, so it was not enough, but there is also one trick that can be used to help. The third line, I will probably skip it, because the fourth line establishes the result that makes the third line irrelevant. The fourth line is one of the 2 main results, is that on 4x4 regional game size, the tile 256 turned out to be reachable. And this computation with maximum layer size slightly above 1 trillion positions requires a bit more than half a terabyte of RAM. In this case, the computation was sponsored. We took a large server which featured a lot of RAM.
So it actually has that many RAM available from one processor, or it somehow.
Yes. I've seen some industrial servers. Okay, I haven't seen, but I've heard of people using some servers with 16 terabytes of RAM maximum. But in this computation, we used this server. It was already pretty big, and it featured almost 600 gigabytes of RAM. Okay, in order to compress the layers to 1 bit per position, we have to come up with an algorithm to. Okay, let me.
No, it's normal to have 1 bit position. You have winning or losing for position.
Yes, of course, but you have to solve the indexation problem inside this layer. That is, you have a layer of constant sum, say 562, and it's an array, a very large array of bits, and you have to. For each bit, you have to be able to understand which position it corresponds to, and for each position, you have to be able to understand which index it has inside the layer. So the following 2 problems have to be solved in order to use this encoding. These problems were trivial before, where we didn't have some constraint, because indexation in the global graph is easier. For example, you can store these bits just in one large array and say that, for example, your largest available allowed tile is 128. That is, you allow nothing to be in itself, 2, 4, and so on and so on. And
so you just need some fixed amount of bits for each cell, and that makes a uniform indexing. But now you have a requirement, so you need to be careful or make some special trick of mapping, numbering the positions.
Yes,
I have a question. Why do you need the opposite procedure? So I understand that given a position, you have to determine its index, and why vice versa.
But you need to look in the table. How can you look in the table if you, for a given position, if you don't?
No, I mean, why do we need a position given by its index?
Okay, but the move is explained in terms of positions. And
yes, it looks like if we just use the index to.
Then the transformation of positions is not immediately available with indices.
Yes, but our algorithm, it looks like we have a position, we have not its index, just a position. We go through all possible other positions on the next layer.
Yeah.
Then yes, so we draw.
And we should look what we know about these positions in tables. So we need to compute indices.
Yes, then we have to compute indices. And why do we have to compute position given by its index?
Because we need to fill some place in our layer, and this place is defined by the index. So first, knowing the index, we need to compute the position. So to find out which positions are obtained from it by the rules.
So it's needed only to iterate through the positions of fixed sum.
And the iteration is not trivial. I mean, you have to do it in parallel. For example, 96 cores were on that server. And so you split this range of integers into batches and give them to different cores. And it turns out that different batches are of different complexity or hardness. I'm not sure which part is. But it requires different time to process different batches, even of the same size. So you can distribute them not according to their number, but according to some hash of the number. Okay.
No, the last remark I don't understand, but probably it's not important. Just continue.
Yes, I'm showing the. Okay. This can be solved using another dynamic programming. An auxiliary array, in fact, small array, which can, given a number of cells and a sum of tiles on them, tell us what is the possible number of ways to fill, what's the number of ways to fill these many tiles with either empty cell or a tile. For example, I 10 to 182 is the number of ways to fill 10 tuples where each cell should be either empty or a tile, 2, 4, and so on, and the sum of tiles should be 282.
So what you are saying, that first you just number the positions just literally from left to the right in the tree. But for fast computation,
I just used graphical ordering, and it turns out that the problem of indexation using this ordering is it can be done efficiently using dynamic programming.
So you need to know when the subtree's boundaries are, so to find where to go, and to compute these boundaries of subtrees, you use dynamic programming. That's what you are saying.
Yes, but the subtrees there are few types of subtrees that can be present, several thousand types. I mean, the number of remaining cells, something not more than 16, and the sum of the remaining cells, something not more than some thousands. So we have to fill that array, recompute it, and then we will use it during the indexation.
Yeah. But the array itself is quite small. It fits in the memory easily.
Yes, it even luckily it gets to the cache. It seems some good cache. I don't know. I have even tried to put it in the smallest cache that it fits in when I was programming for GPU. But it turned out that somehow it started to work slower than if I allow it to use caches in whatever way it wants, in whatever way it wants. So the compiler is more clever than me in this problem. Okay.
And so this big server was with the GPU or it's a GPU?
No, it was only CPU.
It's only CPU with the big memory. Yeah. Okay.
Yes, there was another machine. It was available to me. It was not sponsored, the second machine computation. And this machine, it lacked that much memory, but it did have a GPU. So I had a program for CPU only that uses some threadings. It uses threads to compute on CPU, and another program that computes using GPU. And on the first server I used the first program, and on the second machine I used the second program.
But the result, about 256, is obtained only using CPU and without GPU, large memory.
Yes,
okay.
But it requires large memory.
Okay.
Okay, so this auxiliary array is in fact small, and its values can be computed through one another. It is a dynamic programming problem. Here's the formula how we can find an index, the index of a position inside a layer of fixed sum. I will explain what happens here.
No, I think it's more or less. No, I guess we understand more or less what you should do and what type of the formula, but maybe we can believe you that you can compute it by dynamic programming in this way.
Yeah, basically,
if you start doing
right.
Dynamic programming, just knowing that it's possible, probably you will get this formula quite straightforwardly.
Yes, okay. I also had an example of how this formula works for a small example, but we can also skip them.
Let's skip it.
Okay. I want to say that profiling my program, determining in which functions it was spending the most its time, revealed that 60% of the time it was doing either indexation in one direction or in the other direction. So in these functions, it spent 60% of the computation time.
Mm-hmm.
So most of the time.
So which means that applying a move is quite easy. Difficult is translating it to index.
Yes, I think it's more. Yes, it seems to be more difficult. And yes, you have to do this for all the 500 trillion positions. For each of the positions, you have to use such a formula, and then if there are many edges outcoming of the position, and there may be up to some dozens of edges, you have to compute solve the same problem again. So the number of times you have to solve this problem in order to prove the bound is somewhere in quadrillions, so thousands of trillions.
Can I have a question? So have you tried, so it's like an idea how to boost the application of a turn. So you can, for example, consider, suppose it's turn downwards, and you can split your 4x4 table into 4 columns and do it independently and pre-compute the results of each turn for each possible column, and then just merge these results.
No, we made so many efforts to reduce everything to 1 bit per position that pre-computed.
I mean, it's like it might boost up the procedure of applying the turn, because now we have to do it every time when we go through, calculate the layer, but we can do it in advance for every possible combination of 4 numbers, like corresponding to a column. Like for each column, we pre-compute the result of the new array after applying the move.
But this we still need to transform it to index.
Yeah,
so
but
if most of the time is used for indexing and de-indexing.
Yes. I mean, it would boost up the 40% part.
Yeah.
Okay. Yes.
Okay.
Maybe you are right. It seems like I understood your idea. I'm thinking.
Mm-hmm.
And this is just the program explaining how you go from position, and if you know the sizes of subtrees, then you can move you find the position knowing its number from left to right in a layer.
Yes, the previous formula was for finding the index of a position, and this is for finding the position by index.
Mm-hmm. Okay.
So there was a formula, and here an algorithm. There are some kind of inverse for each other. Okay, here is the diagram, the graph I wanted to show. It answers the question about a peak. On the x-axis we have the sum of the layer. For example, 1,000. And on the second axis we have the number of positions, the size of that layer. You can see it is in trillions. For example, and we can see that the largest layers are around the sum of 500.
And there are dozens of layers where it's close to the maximum. So
yes, and in particular there are 3 consecutive layers. Sorry?
So there are big chunk of large layers. So you cannot make a tunnel algorithm which makes full search to switch from small layer to small layer, skipping the maximum one. That's what I tried to ask before.
Okay.
Now it's impossible. Looking at this picture, we see.
And in fact, it resembles the Gaussian distribution, the probability distribution function of the normal distribution, and there is a reason behind that. In fact, because what this graph, what this function represents, it's the number of ways to obtain a sum of 16 numbers. Each of the number can either be 0, 2, 4, and so on. And if we consider the random variable, which can take values 0, 2, 4, 8, 16, and so on, with equal probability, then this function is the distribution after normalization, is the distribution of the sum of 16 such random variables. And so by something similar to a central limit theorem, we have that the distribution resembles normal distribution, even though the variance of one variable is pretty high.
It somehow look a bit skewed. To the left and right sides are not exactly symmetric, but probably
because of the large variance of one random variable.
Yeah. Okay.
Let's switch to this table. Shows which bounds are available, which are proven. So a number, say 128 in this position, says that it tells us that on the 3x5 field, the maximum tile that's guaranteed achievable is 128 and not twice as much. These all numbers are proven results. And the question mark is the most interesting it is the number for which we have a lower bound of 256 by means of a large computation. In fact, when I was looking at the table, we were looking together with Vladimir Podolsky, and we conjectured that probably the number where the question mark stands is not very large. Probably it's something like either 128 or 256. And we decided to compute for 256 because this computation was necessary in both cases. And it turned out that 256 is reachable. And therefore, to solve the original problem of whether the probability is exactly 1 or lower, we have to check the game for 512.
Yeah.
Yes, but this game is too large to handle. Even in this sponsored computation with goal 256, the number of positions is well, in each cell you can have either an empty cell or 2 to the first, 2 to the second, or and so on, 2 to the 7th. That is 128. And there are 8 options. So 8 to the power of 16 and times 2 because you have user and computer turn. This gives us about 500 trillion positions. And this is the size of this graph, and we have been computing for 4 months on using this 96-core server. But it turned out later that using GPU we can hope that 512 will also be computed. I will explain a bit later.
Yeah. Okay.
But here are the numbers.
Yeah. Okay.
So
how much did it cost, for example, on Amazon, such a thing? Just to get some idea of it's like 1,000 euro or million euro or 10 euro.
No, of course, thousands. It was, as far as I remember, approximately $4,000.
Mm-hmm.
So it was pretty costly.
Yeah.
Yes, and this is why we didn't try to perform the same computation for goal 512 because it will cost even more money. We didn't even make a request, but thanks to the laboratory for accepting this request. Yes, for goal 512, we now have a similar but another approach which will make it feasible probably without using large sums of money. Probably even cheaper than that.
Just continue. Yeah, sorry.
Yes, so 256 is reachable in 4x4. Then I decided to use GPU on another machine which was available to me. And this second machine was not through the laboratory. In fact, this machine was not in the cluster of Faculty of Computer Science or Yandex. Okay, this machine had 24 cores, 64 gigabytes of RAM, so not that much. One very fast SSD solid-state drive disk with speed of 3 gigabytes per second. That's very, very much for disk. And the most powerful gaming GPU available, it has over 16,000 cores and speed of memory of 1 terabyte per second. So this an immense computing power, but there's a limitation that it only has 24 gigabytes of that memory, and we want to have hundreds of gigabytes. So we had to do some tricks. The computation for 3x5 took approximately 2 days for the same goal, but this graph is only 8 times smaller than that graph. So we can see that that computation on CPU took 4 months, and this 8 times smaller computation took only 2 days. So there is large hope that advancing our techniques for GPU-based traversing of these graphs, we can prove more results than currently.
But I don't understand. So if you don't have, if things are not put in memory, then what you can do probably with GPU is that you can compute faster these indices.
I will explain. In fact,
memory access is still slower since it's
yes, it is. There are some technical things to be said. Okay, but this will be in part 2. In fact, we have already 1 hour passed, so I will speed up a bit. Let's take a look at the human strategy of how people usually win this game. They usually make something, for example, like a snake of numbers, or line or row under row. So they collect the largest number in the corner, the second largest next to it, and so on. So that, for example, the topmost row contains the 4 largest tiles, or, for example, the leftmost column, symmetric way. There is a problem with this strategy, although it allows people to win 2048 with high probability. But there is a drawback here in the strategy, which doesn't allow it to reach very high numbers. One of the 4 moves is very unfavorable for this strategy. And in this case, it's the downward move. Whenever you have your 4 largest tiles in the topmost row, when you swipe down, okay, it's just a very bad thing usually. Maybe you can try to play this game, and if you follow this strategy, you can try to make a move down, and you will see how it will most likely break you anything. Because the tile will appear
when the numbers going down form some kind of a snake. It's what you really want, or it's just.
This is an example. Yes, this strategy is not suited for moving down. It is a very bad move for it. So you should always avoid moving down if you are using this strategy.
And moving right is okay.
Sorry?
Moving right is okay.
In most cases, but for example, if you have 3 large tiles here, here, and here is the end itself, then moving right is also not suggested, because you have to store your largest tile in the corner, and it will move from the corner in this case. But usually your first row is filled during play, so well, swiping right is much better than swiping down usually using this strategy. Okay, there is a drawback that we can't use one of the 4 moves. We can almost never use it. Let's take a look at the computer strategy. Here's the screenshot of how computer plays this game. Some decent strategy that was visualized. We can see that it also stores its largest tile in the corner, in the second largest tile next to it, but the third largest tile is not in the same row or column, but it is in the second neighboring position to the largest tile. You can see how it arranges its tiles in a pretty interesting way, favoring corner.
But what is not clear when you say computer strategy? You mean you develop the strategy, or it's kind of usually people use this for computers and obtain some result?
It's the second option. It's not my strategy. It's something that is, for example, revealed if you compute by brute force, for example, 3x3 version of the game, and you then look at the optimal strategy, play with it, and it turns out that it does this thing. It uses the 2x2 corner square to hold its 4 largest tiles, for example.
So you can compute the optimal strategy that maximizes the probability, and this
for
strategy,
3 by 3, yes,
yeah,
and it will reveal the
it
same.
looks like this kind of observations that they move to some corner.
Yes, and for 4 by 4, some people added this to their heuristics, and some people trained neural networks. In both cases, as I know, okay, I'm not sure, but it seems like the strategy is not only from this observation. It's not only found this way. It's also something that neural networks learn by themselves if you try to learn them in an accurate way. So it's a superior strategy to that humans use.
May I have a question at the moment?
Yes.
So at the previous slide, we saw that the human tries to keep some position completely free from the numbers. So it's top, bottom right corner. And the next slide with the computer, we see that everything is filled with the numbers. So if we try to ask the computer what happens a few steps before, would it keep these empty cells in the top right corner and bottom left corner, or it's our own idea of how the computer plays?
It may seem that it prefers not to leave free cells, but it's not true. It's just I inserted not the very best example. It's in fact this is an example of okay. Computer sometimes uses free cells. In fact, during most of its play, some cells are free. I don't know, maybe 1/3 of the cell, like with human players. So this illusion that computer doesn't leave any cells free, it's wrong. Just I inserted the wrong pictures here.
Yeah, if there are few free cells, then there is probability that you can get stuck if something is put badly in the cells by chance. So it's natural to have an idea to have more free cells.
Yeah, but the question was whether we want to keep all these free cells
in some specific place on the board,
or we can have them split. So here it looks like we would have them split into 2 corners. So when the game is played, we move the numbers so that we keep the small numbers in 2 different corners, or it's a wrong idea.
In fact, let's consider the layered structure of this position. That the 1 by 1 corner contains the largest tile. The next layer of 3 tiles contains the 3 next largest tiles. The next layer contains the 5 next largest tiles. And in fact, you can see that inside one layer, it places the largest tiles not in the corner of that layer, but in the how to say it. But well,
just say in Russian, we'll translate. If
но я и на русском тоже не очень понимаю, как сказать нормально.
Cannot help.
Well.
Okay, let me ask a specific question. So is the strategy greedy in the sense that if there is immediate move which allows to combine 2 tiles,
no, it turns out
always done?
No, it's not greedy. In fact, I have made a program that allows one to play 3 by 3, and the program then tells you when you make a move which loses at least, for example, 3 or 5% of the expected score. And this program helps me to understand that many things I did when I was playing this game before, I was doing wrong. And in fact, about greedy, it also turns out that computer is not greedy. Sometimes it tries to to leave two same tiles near one another, just not making the corresponding swipe to merge them, in order to save the possibility to make a new move when it gets stuck. Because sometimes you want to make no move and just get a new tile. And the computer sometimes it leaves two same tiles near one another just
to keep this possibility to get out.
Yes, when it gets stuck, it merges these two tiles and it gets one additional new tile in the position, and usually it helps to get out of the stuck position.
Okay.
I can share the 3x3, although it's a terminal version for console. This version allows you to play 3x3, and computer will point you whether when your turn is at least 3%, or I don't remember, far from optimal turn.
Yeah.
This way you can
it's interesting.
learn
If
how to play.
You don't need GPU or big memory for trying it. It would be fun.
Yes, for 3x3 you don't have to have GPU or large memory.
Yeah. Okay.
Okay. How can we prove that there is a high winning probability reaching some tile on a field, a fixed size? The idea is to fix a subset of positions, a small subset that can be stored in computer's memory, and traverse only their graph, making all those positions outside this subset, pretending that they're lost. So this, if we compute as if our game was the game of that small graph, and all the moves all the edges that point out of that graph, of that subgraph, to the rest of the graph, all these edges lose the game. If we only consider this subset and compute the probability, we will get a lower bound on the probability for the original game. Intuitively, we are computing the probability of winning, staying in the subset. For example, if we have a subset of 1 million positions, we can construct the graph of these positions, and some edges will point out of that subgraph. In this case, we will say, okay, we lost the game.
Yeah. So you only need this subset be a subtree and contain the initial vertex, and then you just going outside the subtree is always a losing move. Then it has smaller probability than
as good as possible subset that fits into our memory. Good in terms of the probability that you will win staying in this subset. How we can do this? The first idea was to take a well-playing strategy, for example, that one that reaches 32,000 with good probability, and sample many rollouts, like playouts, with this strategy against random. And this way, we will collect some useful positions which appear during the game if we play like this very good strategy. And
two obvious problems. First, you need very huge number of tries to fill a reasonable subset, and second, you need indexing, and how you achieve the indexing if you don't have some description of the subset.
For indexing, the problem is, okay, you can just say that, for example, if you have 1 billion positions, then, for example, you can encode them into numbers in any way, like, I don't know, some numbers with at most 18 digits. It can be done easily. And then you can put all these numbers into a large array, sort these numbers, and then when you want to when by number, this number is something like a code of a position. It's not the index in the array, but you can then find whether the position is winnable or not by doing a binary search in this array. It's just an example, and there are better strategies using hash map.
Okay.
So this problem can be solved, but yes, it would require some. Yes, it would cost some computational resources. But yes, there is a bigger problem that you will only cover a small subset of all possible positions. And is there really a hope that your small subset, which you can generate, will be already large enough, that your computer memory will be already large enough to fit a subset which can allow you to prove a good lower bound? And it turns out that almost yes. Let's take this strategy of Heng Hong Xu, which achieves 32,000 80% of the time. And okay, I downloaded the strategy, compiled it, conducted some experiments, made some parsing of its logs, and so on. So I made the sampling process automatic. And I've played about 1 million games on my laptop this way. And about 1 billion positions were encountered there. But here we can see this graph represents whether the number of unique positions in when you generate some positions, of course, they start repeating from some point. So the more you generate, the more the fraction of new positions that you have already encountered. And here's the graph. The blue line is the identity, and the orange line is the dependence of the number of unique positions on the number of all encountered positions. So, for example, when you generate your first billion of positions using this algorithm, and then you filter and remove all duplicates, you find that only 200 million positions are unique there, 1/5. And of course, it becomes worse and worse. So the sampling procedure becomes inefficient when the positions start repeating frequently. We found that we estimated using some other graphs that one can prove a lower bound of around 0.9 for the winning probability in the original game. That is lower than what I have obtained. If you generate slightly above 1 billion unique positions, and this requires around 1 month of computation time with a server of 100 cores. So it's pretty costly, and this will only prove 0.9. But nevertheless, this probability jumps drastically from the probability if you have sampled only, for example, 10 million, not 1 billion positions. So if you sample 10 million positions, that's not enough by far, and what you prove is something like 0.000 and so on.
Yeah.
And if you sample 1 billion positions, what you prove is something like 0.9. So this is approximately what we could get if we went this way. These are our estimates based on smaller computations and how the not shown here graphs behaved. Okay, so we decided to stick to another idea. Another idea was pretty simple, in fact, and it allowed us to prove 0.99969 in just around 2 days, but using a GPU. The idea was that we can look at how computer plays, and then we can simply say that our subset, again, we will construct a subset, a small subset of possible positions. But this time, okay, in the previous, when we were sampling these positions, 1 billion positions, the heaviest part of that algorithm was the sampling procedure. That is, you really have to run their algorithm that plays the game 1 billion times. And this is why, this is where is the bottleneck. You can't run it, for example, 1 trillion times. But you can, for example, consider 1 trillion positions, not running algorithm on them. So if we chose a subset based on another criterion, that so that this subset is easily generated without running a heavy algorithm 1 billion times,
and still small enough to fit in the memory.
Using the previous technique, the trick that splits the graph into layers, yes, it can't. No, it can't fit in the memory even using this, and I will explain a bit later how to solve this problem. But it almost fits into memory. These are the upper bounds we imposed on each value. For example, the value in the corner should be at most 1024, so it could be arbitrary. The second should be at most 512, and so on. You can see that there is a pretty strange structure of these numbers, these upper bounds. This structure was okay. It is the result of experiments on smaller fields. So we have conducted many experiments on smaller fields, and we found that this is what these are the bounds that are needed for each cell in order for the generated subset to be small enough but good enough.
Yeah. So anyway, if you after you invented something, you just use it. If it's
yes, and we also modified the goal. The goal was now to
so hello. It seems it's my problem, or nobody has sound.
Oh, we'll have this problem.
Okay, we can use this time to think about next session. There was an idea once to have the talk of Rustam Zavgarov. So if you are here, maybe you can say whether it's convenient for you to give the talk next time.
I am here. I'm not sure whether I will be prepared for the next Monday.
Okay, and in 2 weeks it's better, or it's still bad?
I don't know.
Okay, so when you will feel ready, then tell us when if at some point you know when you will be ready, then okay. Tell us so we can plan something. Also, there's another talk which is in plans, but I also don't know whether it will be possible on the next Monday. Not also, I don't know whether it's possible for next Monday. Is Maxim Babenko in Yandex? They did something like some kind of common infrastructure thing, like MapReduce for now, and they put it in the open source. And this is a kind of, I think, a big step for them. So he agreed to explain what is the system, what they are doing, and what they achieved, and so on. But also maybe we can ask some informal questions. What are the plans? What do they think about machine learning? How it's important, and so on. But this maybe will be in the next time, maybe 2 weeks. He said that it's possible in April, but we didn't agree on specific date. Okay, anyone, by the way, maybe anyone also wants to give a talk at the seminar and has some idea what it could be about.
I'm sorry, can you hear me?
Yeah.
Good. It seems like I had some internet issue.
Yeah.
Okay.
But we cannot see now the slides.
Yes, just a second.
Yeah. Yeah, slides are okay.
Just a second. I don't know why it is not full screen.
No, it was full screen. Yeah,
okay.
Now it's full screen.
We have redefined our goal to be the following. This was done to reduce the size of the graph, of the game graph, because now we don't have to allow computer to construct to make two 1,000 tiles near each other, because making two 1,000 tiles near each other requires increasing this upper bound in many cells. So we have changed the goal to the goal of reaching these 5 tiles in exactly these positions, and no matter what is in the other cells. It can be proved, but it is not as obvious as it may seem, that this position is winnable, no matter what is there in the remaining cells. For example, if the first row is, if there are no other tiles, then it is obviously winnable. You can swipe right, then up and right. But if, for example, here is, let's say 2, then you can win, for example, by swiping right, and then doing left, right until your two 512 align, and then you make swipe up and left.
Okay,
and so
we cannot follow, of course, but you make some case analysis, and this case analysis is manual. You don't need any computer. You just consider several cases manually. Yeah.
Yes.
Mm-hmm.
So the target was reduced to that. It may seem that it is maybe harder to get exactly these 5 tiles in these positions, but it turns out that no, on smaller fields, this doesn't impede the probability of winning if we constrained our goal to be achieved exactly in this strange way. And in particular, using some kind of these upper bounds for each cell.
Mm-hmm.
So we have heavily restricted the states that are allowed, but still the graph is pretty large. And okay, I will say it a bit later. Just wanted to say that we decided not to use floating point numbers in this computation, because although there is a standard on how these numbers are rounded, and something like only last bit of the result of, say, multiplication is maybe wrong, something of this kind, there are strict standards, but we decided to use integers instead in this computation, because it's easier to follow which lower bounds we can exactly guarantee in each cell than if we use floating point numbers. Because floating point numbers have rounding, which has tricky rules, and so we decided to use integers.
Okay.
There were 3 candidate types: Unit 16T, Unit 32T, and Unit 64T in terms of C++ or CUDA or C. But there are simply unsigned integer types that have 16, 32, or 64 bits. For example, the first type can is capable of storing integers from 0 to 2 to the 16th minus 1.
Yeah, that's what I understand, I guess. Yeah.
Okay, and the probability is stored in terms of fractions of the corresponding power of 2. Say for the first.
You just keep some number after the binary point, and that's clear.
Yes,
okay, so
the first, say 16 binary digits after the point.
Yeah.
And in this format, it was straightforward to understand where we have round to the lower. Okay, in this format, it was straightforward to write code in such a way that it can guarantee strictly that the winning probability is at least as safe.
You just approximate from below if there is no exact value. Okay.
There is also one thing that you can't express exactly one using this format, but it is not important because you can express a very close number to 1, and so this won't worsen the probability. It turns out that UN16T is not precise enough, and because our graph has thousands of layers, on each layer we lose something like a rounding error of around 1 by 2 to the 16th, and if it accumulates along thousands of layers, we lose very much, something, some percent of the probability, maybe several percent, a lot, we lose a lot. So UN16T was not sufficient, was not enough. UN32T was the best fit, and 64T showed almost no increase in probability. So we decided to use 32-bit type. And now the last point, maybe I will finish. The last point is that the graph, even by layers, doesn't fit into memory. And in particular, it has to fit into GPU memory because we are processing it on GPU. So 3 layers don't fit into GPU memory. 3 layers, they were, at maximum, they were 200 gigabytes. And GPU memory is only 24 gigabytes. So they don't fit by approximately 10 times. And that's the problem. This problem was solved in some way, but this way, this has reduced the speed of the computation by about a factor of 10. But because the GPU was so powerful, it nevertheless allowed us to compute what we wanted. This is how it was organized. Well, imagine that your 3 consecutive layers don't fit into GPU memory, but they fit into RAM memory of your computer. Say they are at most 20 gigabytes per layer, so 60 gigabytes per 3 layers. What you can do in this case? Well, in this case, there's a trick that I employed an interesting function in the CUDA programming language, which it tells the compiler to deal with the problem by itself. So the compiler has to manage its whether the data is on the host memory or on the GPU memory. They are physically different, and it moves the data between them. In fact, it turned out that in an efficient way. Of course, there was a slowdown. It turned out that the slowdown was about by a factor of, I don't know, 5 when we switch from GPU memory to RAM memory, but compute on GPU. So it loads chunks of data from RAM of the computer to the GPU memory, then processes them, and then loads them back. It takes the next chunks, and the speed of RAM is about 50 gigabytes per second, and the speed of GPU RAM is about 1 terabyte per second. So they differ in 20 times. But nevertheless, it managed to to compute it pretty efficiently, losing a factor of 5, I would say. And in this case, the computation would be memory bandwidth bound. But that's not the real problem. The problem is that our 3 layers take 200 gigabytes and they don't fit even into RAM of the computer. And that machine unfortunately didn't feature 600 gigabytes of RAM and so on. It only had 64. So the following algorithm was used. It's an algorithm on how we can split layers into batches and load and offload these batches between RAM and disk. So we had kind of 3 layers in the hierarchy of memory. The fastest layer is the GPU. Okay, I can maybe annotate this. The fastest but the smallest layer is the GPU memory. It is insanely fast, but it has only 24 gigabytes. The second layer is the host memory. It is larger, it is 64 gigabytes, but it is 20 times slower. And the next layer is the solid-state drive, which is for disk, it's very fast, but compared to memory, it's again very slow. It has, I don't know, 1 terabyte approximately. And the speeds are, here we have 1 terabyte per second. Here we have about 20 times less, 50 gigabytes per second. And here we have, although the disk is very fast for disks, it is very slow compared to RAM, 3 gigabytes per second. So we were kind of throwing data between these layers, and this connection was handled by the CUDA compiler and all that infrastructure around GPU computing, not by me. And this connection, I handle this splitting layers into batches of size that feed into memory and loading these batches in the right order. So this is how this was solved, and we lost something like a factor of 10 in the speed. And the computation is now bounded by the speed of the disk. That's all.
Yeah.
I would also say a bit about future plans, just a few minutes. By the way, does anybody have questions?
I have a question. What is the bottleneck of your algorithm? Is it disk or is it GPU?
Yes, in this case, it is disk.
Okay.
It turns out that GPU is not fully loaded with tasks. The memory is full with data, and maybe there is a bottleneck here. I don't know, because this part is not mentioned by me, but by the NVCC compiler. I don't know the details of how it managed to move chunks of data between these two parts, and I don't know whether this part is bounded. But I know for sure that in this part, we have our limitation, because disk was almost always reading at 3 gigabytes per second during the computation. And sometimes writing at 3 gigabytes.
Do you store zipped versions of layers or not?
Not, but I don't understand how it would help, because, for example, you store that compressed version of your on the disk, but then you load it to RAM, and then you have to expand it using, for example, gzip inside your RAM. And
no, I mean, maybe you should get rid of disk. And, yeah, maybe you should get rid of disk and store all bits in a compressed way, like by.
But your decompression speed is not that high. It is. I'm not sure that the decompression speed is higher than 3 gigabytes per second for standard archive.
Okay. Because like the simplest way to compress is just shrink the same, like the segments of same bit.
But in some cases, it will, where the layer has approximately half the zeros and half the ones, in this case, it will increase the size of layer considerably. But if you use, for example, gzip or some tool that will compress your data, then it will almost always decrease your size, but it will not work that fast as you may want.
Okay.
So gzip works like something a bit more clever than Hamming coding.
Well, you can try to prefetch the compression.
So you propose, okay, the compressed files are stored on the disk or in the RAM?
Let's say in the RAM.
Okay, here are all our compressed layers. So there are 3 of them, but I'm not sure whether they will fit there because the uncompressed size is 200 gigabytes. So you have to compress them in 3 times. Well, it's not obvious whether it will succeed or not. By the way, you have to store not on the. I don't know. You have to store something like 4 chunks. One chunk is the uncompressed. No. You have to store sometimes you have to store 2 uncompressed chunks and 2 compressed. It seems like it won't fit into 64 gigabyte memory. Okay, maybe it should be tried, but I'm not sure whether it would work because it seems like compressing 200 gigabytes of this binary data will not result in something very small, maybe some dozens of gigabytes in those layers where no, there's a problem. You're proposing this assuming that we have something like a constant density, not very close to 1/2 of ones in our layer. But there is a problem. We're storing not bits, but floating point numbers. Okay, integers. So
yes, but then
they are not compressible adequately. Okay, let's switch to the next slide. How to close this thing. Future work. I would like to try to prove that 512 tile is not reachable. That is the second layer length of 4x4. This requires almost 2 terabytes of RAM, but we will use, of course, the trick with disk. But even with this, we have difficulty because this algorithm of loading and unloading batches, it is unfortunately quadratic. When you are processing a layer, it depends on some previous layer, and you have to consider all pairs of groups of edges between these 2 layers. And the number of these groups is quadratic. And for each of the group, you have to load or offload something to your disk. Let me draw it. For example, you are processing a layer using, let's say, just 1 or not 2 layers for simplicity, and you have split it into 3 chunks that fit into your memory. Then there are edges, these edges, which have to be considered, these edges, and so on. There are 9 types of edges, and for each type of edges, you have to load the corresponding sub-block into your memory, and this sub-block, and the number of times you have to do that to load this from and onto disk is quadratic on the layer size. So in this case, we have the largest layer size of around 60 gigabytes and memory size of 60 gigabytes. It means it allows us to make one block of around 20 gigabytes. There is really not that much overhead. The number of blocks which you split into is something like 3. But for the next computation, we would like to make, where we would like to have 2 terabytes of RAM simulated by disk. This would be a problem because it would not be 3, it would be like 30. And the complexity of algorithm will increase 100-fold. It will not become feasible. It will become infeasible. So there are some difficulties here, but we can split the graph even further into arrangements of positions by set of tiles which are present in the position. The indexation will become considerably costlier, but luckily GPU power is not our bottleneck. It's the disk bandwidth, so we can increase considerably the complexity of indexation by splitting the game graph into blocks by more complex criteria. For example, a block not of fixed sum, but a block of fixed set of tiles. This block is much slower than the corresponding block of sum, but it is considerably harder to index inside this block. But luckily, the bottleneck is not GPU power where the indexation happens. So it seems like a promising idea. And another goal would be to prove a lower bound for large tiles like 32,000, and maybe to compare these rigorously proved lower bounds with those probabilities that heuristic algorithms obtain. But for this case, the computation seems to be on the edge of feasibility, let's say, because of the strange problem. It's called terabytes written, a disk resource. When you are using an SSD disk, it has a limitation of how much data you can write to it during its lifetime. Its limitation is pretty large, think 1 petabyte, for example. 1 petabyte is 1,000 terabytes. So it's 1,000 the capacity of the disk, for example. And for a usual usage of disks, SSD disks, that's well beyond what you need. But for this usage of this disk, very aggressive usage, you are always reading and writing to the disk, and its lifetime resource gets exhausted pretty quickly in some days. Literally, you have to wait, for example, 1 week, and you can now throw off your disk because its lifetime resource of terabytes written has exhausted. This is almost the case with my disk on that computer, where 2/3 of the lifetime resource of the disk was spent during these computations. So we have requested the laboratory whether they can buy a new disk for computations. But for this computation, this will not help because it will really require many disks to be wasted. It is not the way to go, I think. And of course, there are some interesting open questions which we can't answer now. Okay, the first question is what is the winning probability, whether it's exactly 1 or not. We hope to answer this question in foreseeable future. The second question is what's the asymptotic of guaranteed reachable tiles? Currently, I don't have an idea of how we can approach this problem because our results are the result of computations, and asymptotics cannot be proved in similar ways. So there should be completely another approach to the problem in order to prove something about the asymptotics of tiles that are reachable with high probability or guaranteed reachable. But these are very interesting questions. And notice that it is not hard to prove that the winning probability for each fixed goal tile tends to 1 as the size of the board tends to infinity. That's because, for example, you can win by just almost by making only left, right, and so on moves. And because n is very large, there will exist a row where the tiles will spawn in a favorable way, so that the fixed tile you are trying to achieve will be achieved there. For example, you can throw away all rows where at least 1/4 appeared, and asymptotically, although you will throw away most of the rows, you will throw away work. But it's a asymptotic argument of why it approximately happens that the winning probability for each goal tile tends to 1 is n goes to infinity. So these are the 3 open questions, which I would be very interested to know the results. And only this first one seems to be answered in the foreseeable future by us. That's so.
Yeah, okay. So just a question, technical question. So it seems that this game analysis is well suited to this kind of map-reduce approach. So imagine you have array of all positions and of some layer, not in the memory, but then you produce another array for each position. You make copies and you compute all the predecessors and then attach the data for these positions to all these predecessors, and then you get a larger array, and then you sort it, and then you make a reduced step. You combine all the data corresponding to one position. So it seems that you can just switching from two layers to third layer is kind of map reduce step.
Yes, correct.
Why it is not a way to go?
Well, in your proposed approach, do I understand correctly that, for example, when you have, let's say, this is the array of the layer that has to be computed, and this is the cell we're interested in.
No. You start another order. You have array that you already computed.
Okay, this is the
you have 2 layers which are already computed.
Yes.
And for each of these layers, you for each position in each of these layers, you compute all the predecessors from which position it can be obtained by one step.
Predecessors of these positions?
Of every position in this layer, you can compute all its predecessors.
Okay, but yes, but it is the layer where we already have the values. So why do we do that?
No. We compute values going from large layers to smaller layers.
Yes, and
So
this is an example of
computed for layers n+1 and n+2, and we want to compute something for layer n.
Yes, okay.
You take layer n+2, and for each cell, you compute all predecessors in layer n.
Understood, yes. Okay.
And add labels corresponding to these predecessors. This is what is called map step, I guess, if I understand correctly. I heard once talk about this only, so maybe I may make some mistake. And then
yes, okay. You attach these predecessors to these positions. Yes.
Yeah. So I make a list of these positions of this predecessor with the value.
So the array becomes non-uniform in terms of.
The array becomes non-uniform, but it can be done sequentially. You just read the array from left to right and write it down on the disk from left to right.
Okay, but isn't there a problem that at some of the steps of the stage, namely where you are adding new tile, there are dozens of possibilities because, for example, there are up to 16. Okay, say there are 10.
Okay, dozens of possibilities.
Yes.
Dozens of possibilities.
And
but still,
that's why this size increases, let's say, 24.
No, maybe it's not always increases so much, but
yes, no, but increasing tenfold is corresponds to having 5 states.
I guess with this map reduce algorithm, you can have very large memory. So like petabyte is not a problem.
Well, okay, so is it for CPU or GPU or combined?
No, I don't know how MapReduce is realized. What you need actually is to sort the array. Essentially, the operation is sorting. So when you do this step, then you just use this new predecessor labels and then sort this array according to this new labels. And then you get all the information about one specific processor near each other, and then you one left-right swap, one move from left to right is enough to make the merging.
Yes, but it seems like this array should be in the GPU memory, but it is already.
Reduce is somehow arranged this automatically for you. I don't know whether you need GPU or not GPU. I think there are just implementations on big clusters which do it more or less. You don't need to care about implementation. Is a feasible thing?
Maybe I can I ask, for example, Fyodor Kuyanov, maybe he knows about whether this approach will suit, because he has maybe more experience with it.
Yeah, well, I know that large companies use this approach if they want, yes, to store an inadequate number of data. So they split this data between several hosts, and yes, use MapReduce between several machines. So maybe if you
there are two things: that MapReduce is efficiently implemented for large arrays, and second, this is kind of fact which we believe more or less. And another thing, that it seems that the problem is of MapReduce type. It can be easily transformed in MapReduce sequence. It's natural way to try. But anyway, while you were not here, we discussed the possible talks for the seminar, and one of the talks was of Maxim Babenko, who is the main MapReduce designer at Yandex. And so we can ask first of all, we can ask whether it's feasible or not. And second, if it's feasible, we can try to convince him to run your program as a test on his nice MapReduce machine. Anyway, they need some tests, so why not to try this? Yeah. Okay, any other questions?
Okay, I have a suggestion. So the problem remains to determine the optimal indexing function so that it has some locality in indexing, right? If user makes a move, then this index doesn't change very much, because then you can apply your trick with blocks and it will consume less memory.
But currently, it's not the bottleneck. I mean, the indexation operation is now done on the GPU, and GPU.
No, I mean not the indexation, but if you design this indexation procedure to be local, then all your edges would point to consecutive blocks, and then you can load less.
I understand. You propose to explore whether the layers can be sorted in this way, so that edges are local.
Yes.
It's an interesting question. I haven't tried.
Okay. Maybe you should somehow exploit the fact that when you swipe, it can be done independently by the rows or columns. Maybe it's maybe useful.
So maybe a way to go is to take 2 layers and try to sort with some optimization algorithm this.
So my one idea of mine was to so as you know, yes. So for example, first consider all upwards moves, yes, and then it can be considered as independent set of columns in which this move occurs, and try to pre-compute some indexing only on this column, and then somehow combine these indices to produce the resulting index of the position.
Mm-hmm. Okay.
Yeah. Okay. So let's ask if there are any other questions.
I had a comment about your suggestion in the chat, and
yeah.
Maybe I will just tell you. So it seems to me that the algorithm, when you split the well, you have these batches of your data, and you try to use many cores to to work with each batch, but then to produce the part of the next layer, you need all the other batches. So when you do this on a single machine, then you have all the memory all together. So you have it somewhere stored in RAM or in the memory of your GPU. But if you want to use all these petabytes, then you would need to store them well, between the computers, and then you would need to copy all this data. And imagine you have many processors, and then you have all this data, and the data would be constantly copied between these computers, because you for each computer you would need all the data from.
If the graph would be a tree, it will be better. But if it seems not to be a tree, so it's difficult to split the data between the computers without big. But MapReduce, I think, is free of this problem, because you can sort inside each computer, and then you just make a merge, and merging is done with a reasonable data stream. So it should not be a problem.
But I guess it won't work with MapReduce exactly the way which Babenko does, because probably he uses MapReduce for CPUs only, as far as I know, but I'm not sure. I'm not an expert in how.
No, definitely, he uses MapReduce to very large arrays.
Yes, of course, but for
they
CPUs,
don't fit in one memory.
Yes, of course, for a cluster, but of CPU.
Yeah. So what is the problem?
The problem is that the computation, if it is done on CPU, it turns out to be expensive. I mean, the number of operations that you can do on CPU per dollar, for say, is considerably smaller than that for GPU. But for GPU, you have to have some uniformity of
but
your
you
problem.
You can sort arrays with GPU or not. I think MapReduce people should try to implement this if it's possible.
Maybe.
Okay, let's ask Babenko and see what he says.
Okay.
Yeah, okay. Okay, so the next, maybe Babenko will be the next time, or maybe the after the next. So, and if anyone wants to give a talk or knows someone who wants to give a talk, just if you have some idea, write to some organizers, so we have now free space, maybe next Monday. So it will be a possibility. Okay, any other questions? So thanks for the talk, and yeah, see you next time. Okay.
Bye bye.
Thank you. Goodbye.